In fact, let's look at the implications for fish harvests. We're going to look at, and the colors didn't come out right here, but the white areas on the map in the oceans are going to be pre-peak harvest. And then there's going to be this red color that shows up. Red color that shows up as the year moves here. And we're going to see where the peak harvests were and how big they were. And then it's going to turn pink, which should be this color. And that's going to be post-peak harvest. And let's look at how much the world has changed in the last 50 years or 60 years. You see some little movement here. The dark red is the peak, the year of the peak harvest. And then the pink means post-peak.
Right. So that's...
Look at that. By the mid-80s, we've covered almost of the oceans. Here we are in the mid-90s, and boom, 1999, we're past the peak. Let's do it again, just because it goes kind of fast. So here in the 70s, mid-70s, 1980, mid-80s, 1990. So this is at a time when we had, 4 and 5 and 6 billion people on Earth, and now we're talking about we're at 6.5 now, we're going to go to 7, 7.5, 8, 8.5, 9 in the next 40 years or so. Okay, let's, Don mentioned this question of abrupt or nonlinear changes, and here's an example of that when you look at the Atlantic cod off of Newfoundland. And you can see that over years you can look at the fishing, the harvest in tons, and it went way up in the mid-60s, and then there was a crash in around 80, and it went back up again, and then it crashed completely. This is what we call nonlinear changes, and the question becomes, when you get an ecosystem that's teetering, when one or two elements in the ecosystem are can become so out of whack because we've only harvested this or we've only taken that, it can create a very unstable system, and sometimes it can crash like this. So when we talk about tipping points, we wonder about these kinds of tipping points like this. We talked about this a little bit yesterday. Just want to reinforce this question of loss of biodiversity on Earth. Let's take a look at this. Would anybody like to say what you see from this? Let's look first of all from the distant past. We can look at this is a logarithmic scale vertically. Is that awkward when I'm standing there like that? I have a tool here someplace. Here it is. So this is a logarithmic scale from 0 to 100,000, and this looks at 3 periods: the distant past, the recent past, and the future.
Extinctions per 1,000 species.
Yeah, so this looks at extinctions per 1,000 species over 1,000 years. So how many species became extinct per 1,000 species over 1,000 years? So in the distant past from the fossil record, we see that we had less than 1 mammal species go extinct on average per 1,000 years. Hi.
I'm very sorry to interrupt. I just have this for somebody said this meeting.
Jim Evans.
Future model makes no sense. Looking at 1,000 extinctions per 1,000 species.
So historically we've had a low rate of extinctions, even though we've had periods where we've had huge extinctions, right, Sue? Right, okay. So then in the recent past, we've got much higher level, around in the order of 80s or around 100 extinctions per 1,000 species. And the projection is that it's going to be significantly higher than that. This again comes out of the Millennium Ecosystem Assessment. So the way in which we're doing things doesn't appear to be sustainable in terms of the wealth of diversity, biodiversity of life. Okay, so who's at risk? So we've got an understanding of ecosystems. We understand that we rely on them in substantial and critical ways for our everyday functioning, for the things that we need for life. They sustain our lives. They're not, 60% of them are degraded to the point where they're threatened, and the conditions that might support their health are not really there because our population is increasing globally, and the mean level, the standard of living across the globe is going way up. So we're extracting more and more resources. So who's going to bear the brunt of this kind of threatening condition? Well, Mark Newman at the University of Michigan has got this wonderful website in which he's developed a series of cartograms. This is a map. This is a map that you're familiar with, right? It's a flattened world map, right? A cartogram contorts a map and makes it look different based on not land area but on some variable that you're concerned with. So for instance, we can take this map and using the cartogram idea, we can show world population. So this is what the world population would look like if we expressed the map with respect to the population of the Earth. And what do you see? Shout it out. China, yeah, China and India look really big. Well, what if we did it? What if we looked at gross domestic product? Africa kind of disappears, doesn't it? Look at the U.S. We look bloated. Yeah, look at Japan, right? Yeah. Isn't that fascinating? Okay. Well, since we.
Can you point out your rock on this?
Where's his trap door? Okay, well, we're talking about stewardship here, and we're talking about how Christianity and environmentalists could work together. Let's look at Mark's map on where Christian nations are. So if you mapped Christianity across the world, what do you see? Shout it out. What do you see?
South America.
Yeah, South America is pretty muscular. Africa is pretty muscular.
Oh, yeah.
I'm surprised at China, though. It doesn't seem.
Can you explain the colors?
The colors are just so that we can see the separate countries. Yeah.
Korea.
Okay, so I want us to keep a couple of. I want to keep seeing these things in mind. I want to keep Christianity in mind. This is very hard to do. We need to have a mental overlay, and I've got a sequence of maps here.
Yeah.
So Eric would like to take. Let's just duly noted that Eric would like to take exception to this, to the data that went in here.